On our second day of parametric equations, we're going to be looking at an application of parametric equations, and that is motion along a curve, and it will involve vectors. So let's consider a particle moving along a curve, and this curve is described by parametric equations, so it can be a goofy curve. So we have a starting position, an ending position, and anytime we're dealing with motion, we can have velocity, acceleration, all of those aspects, distance traveled, all of those things. So we have this particle moving along a curve. We can describe the position of the particle with our parametric equations. X of t will describe the x-coordinate or horizontal position of the particle at time t. Y of t describes the y-coordinate or the vertical position of the particle at time t. In straight line motion, displacement was the ending position minus the starting position. Ending position minus the starting position. Now, on straight line, on motion along a curve, the way I drew this, they're kind of on a horizontal path. But let's say that we have this. We want to find in motion along a curve, we're not going to be finding ending position minus starting position, because our curve is described by a pair of parametric equations. We want instead to find just the length of that the distance between those. So the length of that line segment. In parametrics, we can find the magnitude. Magnitude, when you see the word magnitude, think length. So we can find the length of the displacement by finding the distance from the ending position to the starting position. So the distance, let's say our distance between the ending position and the starting position was that. We want to find the length of that. Well, it's easy to do if we write the two components of that length. It's going to have change in x, it's going to have change in y. So the length of that, using the Pythagorean theorem, will be the square root of change in x squared plus the change in y squared. So the magnitude or length of displacement, our notation for magnitude or length is it uses absolute values. That's notation. So the magnitude of the displacement is the square root of change in x squared plus change in y squared. And this is from time A to time B. So change in x would be x at time B minus x at time A. Change in y would be y at time B minus y at time A. And since we are squaring these, since we're finding the length, it really doesn't matter which we put first, the A or the B. We can also describe the velocity of the particle. Back when we did straight line motion, we said that velocity was the derivative of the position function. Still the case in straight line motion. But now the position function has two components. So the velocity must have two components. In addition, the velocity has magnitude. That makes velocity a vector. When we're traveling along a curve, velocity is always a vector. It has two components and magnitude. What are its two components? Well, if our curve is described by x of t, y of t, for velocity, the velocity vector, and you'll see that I always use notation This is vector notation. It means that this variable is a vector. That's how I learned it, so that's what I do. The velocity is a function of time. This velocity vector is a function of time, and the x component of the velocity vector is x prime of t. The y component of the velocity vector is y prime of t, if the position is x of t and y of t. I also use vector notation for my little brackets, I guess you'll say. This is how I learned it, so that's how I always write it. AP, College Board, accepts parentheses or these little, I call these little chevrons. They accept parentheses or chevrons. I learned it as chevrons, so I will always use chevrons whenever I'm describing a vector. Just like I will always use that little vector notation, that is also optional for you. You don't have to use it. However, I will say, students who don't use that notation every time sometimes forget that you need a vector for velocity in particle motion along a curve. Now for the magnitude or length of the velocity vector. Well, this is a vector. A vector has direction and it has length. So to find this length, we are going to draw our x and y components again. What is the x component of velocity? Well, the x component is not changing. X prime of t. It's x prime of t. That would be the x component of the velocity vector. The y component would be y prime of t. So, what is this length? Well, using the Pythagorean theorem, it would be the square of x prime of t plus the square of y prime of t. So the magnitude of the velocity vector is the square root of the sum of x prime of t squared and y prime of t squared. We could have also written x prime of t as dx dt and y prime of t as dy dt, of course. It just makes it look a little bit messier, but we surely could have done that. Speed. Back when we did straight line motion, speed was the absolute value of velocity in straight line motion. That was what speed was. I said speed could never be negative. Well, speed is still the absolute value of velocity, but now velocity is a vector. Notice the similarity in notations. Speed is the same thing as the magnitude or length of the velocity vector. So it's the exact same thing. So we need to know that. Because sometimes they'll ask us for speed, sometimes they'll ask us for the magnitude of the velocity vector or the length of the velocity vector. They are the exact same thing. When we did straight line motion, acceleration was the derivative of velocity, which was the second derivative of position. Just like velocity, acceleration is also a vector. So the acceleration vector will be the second derivative of the x coordinate of position and the second derivative of the y component of position. Next, we're going to talk about total distance traveled. Total distance traveled. So again, we have this curve, and this particle is on this curve, and we want to know how far did it travel. So if we took this and straightened it out and measured it, that would be how far he traveled. the particle traveled. So we've already done this because we already have an equation for the length of a curve. And we did this not for parametrics, we did this for functions. We had the length of a function. And the length of a function we found, and I could derive it, it came from the Pythagorean theorem, and then finding all of the sums, it came to be the integral from x is equal to a to x is equal to b of the square root 1 plus the derivative squared dx. That was our length of a function. Now we want the length of this curve. So I'm going to take that, what we just found. I think I'm going to just, well, I'm going to find it. So this is going to be the integral a to b of the square root of 1 plus f prime squared. F prime is dy dx. And when we derived it, that's what we used, was dy dx. All right, but now we have motion on a curve, we have dy dx, and we know what dy dx is when we're on a curve. We did that yesterday. Dy dx is dy dt over dx dt. Yeah? Which means dy dt squared over dx dt squared. Yeah? Okay, inside the square root, I'm going to get a common denominator. So inside that square root, my common denominator is the only denominator, dx dt squared. 1 is dx dt squared over dx dt squared. Dy dt squared over dx dt squared is dy dt squared over dx dt squared. So I got a common denominator there. Copy down everything else. Okay, now when we have the square root of a fraction, it's the square root of the numerator divided by the square root of the denominator. So in here I have the square root of dx dt squared plus dy dt squared, that's my numerator, divided by the square root of dx dt squared. Well, the square root of dx dt squared is dx dt. I'm going to copy down everything else. Okay. Well, I'm dividing by dx dt. Well, dividing by dx dt is the same thing as multiplying by dt dx. So I'm going to multiply this instead of dividing by it. Instead of dividing by dx dt, I'm going to multiply by dt dx. I still have this dx over here. What happens to the dx's? They cancel out. So we have this equation. Okay. Now, a and b were the values, the x beginning x value and the ending x value. So a and b would be these would be x coordinates, but we want to find the time at that. So this would be the time when x was at that starting spot, and this would be the time that x was at its ending spot. So now these a and b's are t values. It wouldn't be the same as the x's, but these would be the t values. So this is our formula for the total distance traveled. So I'm going to write this in a different way. I'm going to write this as square root of dx dt is the same as x prime of t dy dt is the same as y prime of t. Does that look familiar to you? Does the square root look familiar to you? It should, because we just found that. That was what we found for speed, or the magnitude or length of the velocity vector. So the total distance traveled is the integral of the magnitude of the velocity vector, or speed. From time A to time B. So those are all of our formulas. Those are all of our components that we consider when we are describing a motion of a particle along a pair of parametric equation, a curve described by a pair of parametric equations. Let's take a look at some examples. So in this first example, we have a particle moving in the xy plane so that at any time t, the position is given by this pair of parametric equations. Find the velocity vector when time is 1. Well, the velocity vector is a vector. Its x component is x prime of t. Its y component is y prime of t. So the velocity vector, well, this would be, I'll just write it up here. That would be x prime of t is 3t squared minus 8t. Y prime of t, 4t cubed plus 6t squared. And then the velocity vector at time 1 would be -5, 10. Find the acceleration vector when time is 1. The acceleration vector is the second derivative of x and the second derivative of y. So I'm using my first derivative here, so that we'd have 6t minus 8 and then 12t squared plus 12t. So at time 1, that would be -2, 24. Very good. Number 2. A particle now moves in the xy plane so that at any time t, the position is given by x of t and y of t. For what values of t is the particle at rest? Well, the particle is at rest. The particle is at rest when there is no movement, right? When there's no movement. Well, when does the particle not move? The particle does not move when its velocity is 0. But remember that velocity has two components. So we need for both of those components to be 0. The particle is at rest when the velocity vector is 0, 0. Both components must be 0. So I'm going to find x prime and y prime and set them each equal to 0. So x prime is 6t squared minus 30t plus 36. I'm setting that equal to 0. Solving for t, I'm going to factor out a 6. And then we're going to have two sets of parentheses. And we need two numbers to add to get a -5 and multiply to get a 6. So that's going to be a -2 and a -3. So t equals 2 and t equals 3 are the two times when x prime is 0. That means at those two times, the horizontal, there is no horizontal movement. Remember that x prime describes the horizontal movement. Y prime describes the vertical movement. So now we're going to find y prime of t. 3t squared minus 6t, set that equal to 0, solve for t. So 3t, I'm going to factor out a 3t, we'll have t minus 2. So t equals 0 and t equals 2 are the two times when there is no vertical movement. So when is there no movement at all? Only at time equals 2. So at rest, at time equals 2. Great multiple choice question. What if there was nothing in common? Then the particle would never be at rest. They would always be moving in some direction. Number 3. A particle moves in the xy plane so that at any time greater than or equal to 0, the position is given by this pair of parametric equations. Find the magnitude of the displacement from time 1 to time 2. Magnitude of the displacement. So magnitude of the displacement is just the distance between the ending and the starting position. No derivatives there. This is just the square root of change in x squared plus change in y squared. Displacement just involves position, no velocity. Alright, so I need change in x and I need change in y. So let's find change in x. Change in x would be x at 3 minus x at 1. So x of 3 is 9 plus 9. X of 1 is 1 plus 3. We have 18 minus 4, so that's 14. So change in x is 14. Change in y, what is y of 3 minus y of 1? Y of 3 is 27 minus 27. Y of 1 is 1 minus 3. So this ends up to be 2. So the magnitude of the displacement, would be the square root of 14 squared. I'm going to write out the equation first here. Change in x squared plus change in y squared. So that is the square root of 14 squared plus 2 squared. That would be a safe stop spot. As a multiple choice question, they would have us work that out a little bit. 14 squared is 196. 2 squared is 4. So 196 plus 4 is 200. That has a perfect square of 100 in it, so this would be 10 square root of 2. As a multiple choice question. Answer. Find the magnitude of the velocity vector. Magnitude of velocity vector is speed. And that is another square root, but these two components would be x prime and y prime rather than delta x and delta y. So we are going to need to find x prime and y prime. X prime is 2t plus 3. Y prime is 3t squared minus 6t. We want the magnitude of the velocity vector when time is 1. So x prime of 1 is 5. Y prime of 1 is negative 3. So the magnitude of the velocity vector at, well, first I'm going to do it at time t. And you know what? I should have clarified this. I was finding the displacement here from 1, use brackets, 1 to 3. The magnitude of the velocity vector in general is the square root of x prime of t squared plus y prime of t squared. And now we're plugging in 1 for t. So if we're plugging in 1 for t, x prime of 1 is 5. y prime of 1 is 3. 25 plus 9, that would be a safe stop spot. 25 plus 9 is 34, so square root of 34. Okay. A particle moves in the xy plane in such a way that its velocity vector is this. So they are giving us x prime and y prime. If the position vector at time 0 is 7, -4, find the position of the particle at time 1. So they're giving us x prime and y prime. They're also giving us x at time 0 and y at time 0. And we want the position, so we want the x coordinate of time at time 1, and we want the y coordinate at time 1. Well, if we want x and y, and we know x prime and y prime, in my mind, we just need to integrate x prime and y prime. And we're using x of 0 and y of 0 to find our c value, just one value. So I'm going to set up the fundamental theorem. X at time 1 minus x at time 0 is the integral 0 to 1 of x prime. Fundamental theorem. Remember that 1 and 0 are t values. This is x of t minus x of t, right? They're time values. So x of 1 is what we're trying to find. We know that x of 0 is 7. And we know that x prime is 3t squared minus 4t. So x of 1 minus 0 is equal to, let's find the antiderivative here, little power rule. Raise your power by 1, divide by your new power. Raise your power by 1, divide by your new power. Evaluate that from 0 to 1. And we'll have x of 1 minus 7 is, plug the 1 in for t, we get 1 minus 2. Plug the 0 in for t, and we just get 0. So we have x of 1 is negative 1 plus 7, which is 6. So the x coordinate of the position at time 1 is 6. Now we're going to do the same thing for the y component. Y at time 1 minus y at time 0 is the integral 0 to 1 of y prime. Y at time 0 was given to us to be a negative 4. Y prime was given to us to be 8t cubed plus 5. We're going to integrate using the power rule. So add 1 to your power, divide by your new power, and then the antiderivative of 5 with respect to t is 5t. Evaluate that from 0 to 1. So y of 1 plus 4 will be, if we put 1 in for t, this turns out to be 7. If we put 0 in for t, that's 0. So y at time 1 will be 3. So our position at time 1 is 6, 3. Now, since they use chevrons when they gave me the point, I'm going to use chevrons when I give them the point. However, if this was an FRQ, you could use parentheses or chevrons, and it doesn't matter. And that is our first day of vectors and motion along a curve. Tomorrow we'll do the same concepts, except with a calculator.